Good morning students. In today's topic we are going to discuss about the formation of a PN junction. We know P stands for holes, positively charged, N stands for electrons, negatively charged. So we are taking a semiconductor and we dope one side of the semiconductor with trivalent impurity and other side of the semiconductor with pentavalent impurity. So we will get a PN junction diode. I repeat, we take a semiconductor crystal, dope one end of the semiconductor crystal with trivalent impurity and the other end of the semiconductor crystal is doped with pentavalent impurity. So you will get a PN junction diode. So before moving on to the formation of PN junction diode, we have to discuss about the conductivity of P-type semiconductor and N-type semiconductor. Electrical conductivity of semiconductors. We already discussed the total current of the semiconductor is due to the free electrons, the current due to free electrons and also the current due to the movement of holes. So the total current can be given as I is equal to IE plus IH. We already studied the equation for current. I is equal to NAVE, where V is the drift velocity. So I will write here the current for electron is given as Ne, number density of electrons, into E, which is the charge of the electron, into A, area of cross section, and VE, that is drift velocity of free electrons. Similarly, the current due to holes is given by NH, that means the number density of holes, E for charge of electron or charge of hole, both of them are same, A the area of cross section and VH the drift velocity of the holes. So I just took the equation from chapter 3, I is equal to NAVE, and I just put the subscripts E for electron and H for holes. I got two equations, I substituted both the equations. So I is equal to NEEAVE plus NH into E into A into VH. So that is the total current. Now we already know if the applied electric field is small, then semiconductor obeys Ohm's law. I already told semiconductor do not obey Ohm's law at normal case. But if the applied electric field is very small, at that time it obeys Ohm's law. And then we can say V by R is equal to I. So I wrote it like this. And in these two terms, E and A are constant. So I took EA outside. So EA into NEVE plus NHVH, or V instead of R I can write rho L by A, because the resistance is rho L by A, we studied in 3rd chapter. So I put rho L by A, so A comes in the numerator, rho L by A equal to this, A and A can be cancelled. So the remaining thing is V by L, A and A cancelled, V by L is there and rho is there in the LHS. V by L is called electric field. So instead of V by L I wrote electric field. So E by rho is equal to small e into NEVE plus NHVH. And what is 1 by rho? 1 by rho is called sigma. Therefore, sigma is equal to E into NEVE plus NHVH. Now, here mobility, it is defined as the drift velocity per unit electric field. So this electric field I brought it to the denominator. So VE by this capital E is called mu E, mobility. Similarly, VH by capital E is called mu H. So instead of VE and VH, I just divide the equation by capital E, which is electric field, and drift velocity by electric field is called mobility. Therefore, I just wrote mu E and mu H instead of VE and VH. Okay, you think like this, VE by capital E is mu E and VE by VH by capital E is called mu H. So, our final equations become sigma is equal to E into Ne mu E plus NH mu H. And the mobility of electrons is higher than that of hole mobility. The resistivity or conductivity depends not only on the electrons and the hole densities, but also on the mobility. The mobility depends relatively weakly on temperature. So, in conductors it depends, the mobility depends on the temperature, properly depends on temperature, and we studied there in current electricity, we studied when temperature increases conductivity will decrease. But here the reverse thing happens, when temperature increases conductivity will increase. So, here mobility depends very weakly on temperature. Now, let us move on to our topic, which is PN junction diode. So, as I told you, PN junction diode means when a p-type semiconductor is joined to an n-type semiconductor such that the crystal remains continuous at the boundary, the resulting arrangement is called PN junction. So, we are not literally taking a p-type semiconductor and n-type semiconductor and join it, we can't do that. That is why I told in the beginning, you take a crystal, on one side you dope with p-type impurity, other side you dope with n-type impurity. Now, look at this figure. When a PN junction is formed, we are going to study what happens when a PN junction is formed. When a PN junction is formed, the P region has mobile holes and immobile negatively charged ions. So, this is the P region. You can see P region is having mobile holes and immobile negatively charged ions. That is why I have put the negative sign in the circle. They are immobile, they can't move. But that grey color dots, that is actually holes, they can move. Okay. Similarly, in N region, look at this region. In N region, it has mobile electrons and immobile positively charged ions. So, here positively charged ions cannot move, that is why I have put it in the circle. Whereas, electrons I have put like violet color dots, they can move freely, they are mobile. So, that is why here it is written mobile electrons are there because electrons are the majority carriers. In the P side they are mobile holes because holes are the majority carriers. And this line is called junction. So, at the junction what will happen? So, before saying I am just telling it that the whole arrangement is electrically neutral. That means the total charge of the semiconductor is always 0. Number of positive charge is always equal to the number of negative charge. Now, what will happen soon after the formation of PN junction? When a PN junction is formed, holes from the P side, look at the figure carefully, holes from the P side will cross the junction and move towards the electrons on the N side. Similarly, electrons from the N side will cross the junction and move towards the P side and combines with the holes. So, in this region which I am showing, this region, in this region the electrons and holes are recombined. Electrons combine with the holes. So, imagine like this, holes from the P region diffuse towards the N region, due to difference in the concentration, and they will combine with the holes, combine with the electrons. Similarly, free electrons from the N region diffuse into the P region due to the difference in the concentration, and free electrons will combine with holes. So, in this region, electrons and holes are combined. Then what will happen? What will happen in this region? Now there are no more free electrons or no more free holes, because in the beginning there were some free electrons and holes. That means our first figure, this was the junction, here there were some free holes and here there were some free electrons. They move across the junction, they cross the junction each other and they combined. That means holes here combined with the electrons on this side. Similarly, free electrons on this side combines with the holes here. As a result, a region is created where there are no mobile free electrons or holes. This region is called depletion region. So, depletion region is a region where there is no free electrons or holes. Okay, that is what is written here. The uncompensated negative immobile ions in the P region do not allow any more free electrons to diffuse from the N region. Similarly, uncompensated positive immobile ions in the N region do not allow any more holes to diffuse into the P region. So, what I explained is, after this depletion region is formed, no more further hole can cross this and move towards this side to join with the electron. Similarly, no more further free electron from here can cross this region and join with the holes at this side. Depletion region actually acting like a barrier, so that electrons and holes cannot cross each other thereafter. Okay. Now, you can think, since there are holes coming towards this side, there will be a positive potential here and electrons came from here to this side, right? So, there will be a negative potential here, and I already told this depletion region will act like a barrier. The potential, the intrinsic potential of that barrier is called barrier potential. This barrier potential will prevent the further diffusion of holes and electrons. Okay. So, what is the reason for the barrier potential? Barrier potential is created because there are some holes which crossed the junction and moved here, which created a positive potential. Similarly, some electrons from this side move towards this side, thereby creating a positive potential here. That forms the depletion region and that forms the potential barrier. This potential barrier will prevent the further movement of electrons and holes across the junction. Okay. So, we discussed about potential barrier, and the potential barrier of silicon is nearly 0.7 volt, and for germanium it is 0.3 volt. The potential barrier opposes the motion of the majority carriers. However, a few majority carriers with higher kinetic energy manages to overcome the barrier and cross the junction. The potential barrier helps the movement of minority carriers. How this will happen, I will explain later. Here, one more thing that you have to think. I told no, there is a potential barrier, and the potential barrier will prevent the further diffusion. So, till how much can be the thickness of the potential barrier? That is what we are going to discuss now. So, electrons and holes are crossing layer by layer. Suppose 2 or 3 layers are formed. Imagine like that. There are many layers. So imagine like 2 or 3 layers are formed. At that time, a small potential, positive potential is created here, negative potential is created here. Due to that, there will be an electric field from positive to negative. Okay. Due to this electric field, the direction of the electric field will be in this direction, because positive holes came from here, negative electrons came towards this side. So due to that, in the depletion region, there will be an intrinsic electric field which is from the N side towards the P side in the depletion region. That means here to here. Due to the electric field, the holes from the N side, of the adjacent junction, adjacent side of the junction will jump towards P. Similarly, electrons just near to the junction will drift towards N. This thing happens only just on both sides of the junction, not all these spaces. These all spaces it will not happen. It will happen only for the electrons and holes just near the junction. Okay. So due to the electric field created, due to the intrinsic electric field created, the holes just closer to the junction on the N side will drift towards P. Similarly, electrons just on the side of the junction of the P side will drift towards N. That drifting of free electrons and holes will create a current which is called drift current. Initially, diffusion takes place first, drift takes place second. Initially, diffusion current is more and drift current is less, and as more and more electron and hole recombination is taking place, the width of the depletion region starts increasing. So at that time, drift will also increase. So I will say like this: as diffusion increases, the drift also increases, and at a particular time, at equilibrium, the diffusion current becomes equal to the drift current. Diffusion current becomes equal to the drift current. At that time, the further diffusion is prevented, and we can say a PN junction diode is formed. And till there, the width will grow. And when the drift current becomes equal to the diffusion current, at that time this width becomes stable and it prevents the further diffusion of electrons and holes. That means the barrier potential will be formed at that time where the drift current becomes equal to the diffusion current. So we can say PN junction is formed. Okay, that's all. Thank you.